We have with us Dr. Debattam Dash um, from IISER Mohali. He defended his thesis from IISER Mohali recently. He will be speaking about combinatorial growth of the reciprocal classes in the Hecke groups. Over to you, Devattam. Please begin.
Okay. Uh, so thank you, Shomoda, and thank you, organizer, to give me chance to speak here. And okay, so here you go. So uh, so the title of the talk is um, that common growth of reciprocal classes in the Hegel group. So first of all, I'll just give a brief give a brief survey over the reciprocal classes and what are the works are already done and what kind of work can we do in the further. So okay. So first of all, I need to introduce reversible elements. So later we will get to know these elements are nothing but reciprocal elements in the case of Fuchsian or Kleinian groups. Okay, and after that we will see the counting of those uh, reciprocal classes, and then we'll get to know some results about it. Okay, sorry. Yeah. So what is a reversible element? An element uh, an element of a group is said to be reversible if it is conjugate to its own inverse, and that means there exists an element B such that D inverse G B equal to G inverse, and if this B is an involution, then we will say G as strongly reversible. Okay, and by the definition, the strongly reversible elements are always reversible, but converse is not true. So for instance, you can take uh, an element from SL and symmetric element from SL to Z. So these elements are reversible but not strongly reversible. And and also there is an observation that the strongly reversible element can be seen as a product of at most two involutions. At least for involution is already involution is of course a strongly reversible element it's because you can just product three involutions, you'll get one. So it will always be a strong reversible element. But yeah, so by classifying a strong reversible element in any type of group, that means you have classified the number of you have classified the elements where it is a product of two involution. Okay, and this classification of reversible and strong reversible is a theme is a theme kind of work for any type of group. You can choose a group and try to find out the reversible and strong reversible. What are the strong reversible and reversible elements are? Okay, so since that reversible and strong reversible elements are conjugacy invariant, so we will say the reversible elements are conjugacy invariant, and we can say that conjugacy conjugacy classes of containing reverse element are reversible classes. So the reversibility, uh, as I already told you that reversibility is a theme for every group. Sometimes it is interesting, sometimes it is not. For some group like SL2R, GL2R, SLNC, the reversible reversibility is really interesting. But some other groups like Y1 of SG or this kind of group, there is no reversible eliminator. Okay, so in that case, these groups are not interesting in the sense of in the context of reversibility. And also I guess for SL2R, GL2R, yeah. or I can say PSL2R. These are very very interesting, and we can also see the uh, classification of it. Okay, and these are and diversity of discrete subgroups are also be studied like for SL2Z, GL2Z, or PCL2Z in different point of view. You can check it out that book by O'Fall and Yarshot, Reversibility in Dynamics and Group Theory. I guess that is the name. And Sharnak, Peter Sharnak, he reproved that classification of strongly reversible element from PSL to Z, and he call it reciprocal. So here we take that reciprocal terminology from Sharnak's paper, Reciprocal Geodesics, uh, and uh, and we will say reciprocal instead of strongly reversible throughout this talk. And yeah. And there is a one correspondence between the conjugacy classes of these reciprocal elements and the modular and the of the module in the modular group, and the conjugacy classes of infinite dihedral subgroups containing in the modular group. That means if you find out the reciprocal classes in the modular group, you will you will just find out the infinite dihedral subgroups containing in modular group after conjugacy. So that's why the classification of reversible classes is important for PSN to Z. And also there is a one-one correspondence between the closed geodesics of H2 mod gamma H2 mod PSL2Z and the conjugacy classes of hyperbolic elements of PSL2Z. So here you can so that means there is a special kind there is some special class of closed geodesics which is one corresponding to reciprocal classes. So these geodesics are known as reciprocal geodesics, and these geodesics are actually passed through two-ordered cone point in the modular surface. Modular surface means the quotient of H2 mod gamma KCl to C. So the spaces look like this, but this is a two-order cone point. There is a three-order cone point. So those geodesics which pass through two-order cone point are known as reciprocal geodesics. And Sharnak gave the asymptotic value of the number of primitive reciprocal geodesics for the modular surface. And later, Sharnak, this result is generalized by Larson and Suto for any type of two-dimensional hyperbolic orbifold. That means they have counted the number of reciprocal classes for any kind of Fuchsian group, any finite type of Fuchsian group. I should say. And recently, Parakon and Paula they have generalized Larson and Suto result for in general Riemannian orbifold. And this is just recently, I guess, in 4 months or 5 months, they have uh, they have established that article. Okay, so in our case, in my research, we choose not the hyperbolic length of the geodesic, we chose the word length of the geodesic. So that word length is depending on the pre-structure of that group. Like for instance, we are choosing Hecke group. So what is Hecke group? Hecke group is a fusion group which is generated by iota and gamma p, and it can be geometrically it can be seen as a Z2 star ZP. So there is a free structure here, and for particularly if I choose p equal to 3, so then Hecke group is actually modular group in particular case. Baswaj and Sujivalli, they have investigated that Sharnak result in context of word length. I mean, we later we will see what is word length for geodesy. But yeah, this is the result for uh, which is Baswaj and Sujivalli get that for a primitive reciprocal geodesy with word length less than 2t is the number of that set is asymptotic to 2 to the power t over 2. Okay, so later Marmorejo in her thesis she extends the result for the Hecke group for the odd case and established the result concerning spherical growth. Spherical growth means there is no inequality here. It will be equal to that will be a spherical growth of that. And we further extend Mahamonaja's result for even case and independently Basmaji and Sujivali Mahamonaja they have also improved Mahamonaja result for even case. So okay, so more recently we have extended the result by Basmaji and Sujivali for the Hecke group. This result I mean and by using central limit theorem and from the probability. Okay, so so we'll go to the next section that why the reciprocal element are so there is a theorem by us that for a fusion group or Clanian group, if gamma be a fusion or Clanian group, this is subgroup of PSL2R or PSL2C respectively. So then that element is reciprocal if and only if it is reversible. That means in that case it is reversible if and only it is strongly reversible. And every conjugating element that means if it is reversible then this must have to be an identity an inversion. And for the fusion group only possible reciprocal elements are either hyperbolic or involutions. I mean, or elliptic elements, which are involutions. And if gamma be a Clanian group, gamma be a Clanian group, then the parabolic elements can also be reciprocal. For example, if I take Picard group, that group means PSL2 Zi, where Zi is Gaussian integer. In that case, the parabolic elements are also reversible. Parabolic elements are also reversible. Okay, so first of all, we will try to classify the reciprocal classes in Hecke group. For that, we need to define a special kind of function that is fixed point ratio. So fixed point ratio of A is where is the hyperbolic element is theta A where it is look like B minus C over A minus D or infinity or 1. So we distinguished these two conditions because of we need that this part we will need that in uh, to in our theorem. So and fixed point as fixed point we named it fixed point ratio because of the theta A can be represented as a function of fixed points of A. So that means theta of A to the power n is equals to theta of A. Okay, it is always true for any hyperbolic element theta. Okay, so this is the classification of Hecke group that G for odd case G is either an involution or conjugate to a hyperbolic element which where the lift of the hyperbolic elements in SL2R are symmetric matrices. So this is true for uh, this is true for modular group also. And for the event case, this is either an evolution or conjugate to a hyperbolic element where the fixed point ratio is zero, either 0, 1, or cos pi over t. So 0 means that theta of a 0 means that if I take the first case minus c, so that means d equal to c. Okay, so that means the for that case the this is symmetric matrix ABC. So okay, so now we will see some definition that the an element said to be symmetric if the reciprocators are iota. For example, look like this, and an element said to be p-reciprocal if the one of the reciprocals are uh, conjugate to this. Reciprocators mean the conjugating element, and the reciprocal element is said to be symmetric p-reciprocal if the reciprocators are conjugate to both. So that means it is something like this. Okay. So why we need that definitions? So to state this theorem actually. So these are generalized result uh, of a result of Charnac that for the modular group and every reciprocal class has exactly four symmetric elements. Okay, so for in our case, for odd p, that is true for that is uh, true as the case of modular group, and for even case, there are exactly either there are exactly four symmetric elements, or there are two p reciprocal elements, or there are two symmetric element and p symmetric p reciprocal element, and or there are two symmetric p reciprocal element and p minus two many the p reciprocal element. Okay. To summarize, we have already discussed what you have already discussed, the classification of reciprocal element for Hecke group, and then and the you can say this theorem is actually required for to parameterize the reciprocal element for Hecke group, and so now we'll move to the word length and the representation of reciprocal classes. So from the previous theorem, we already have seen some pattern of it. So we represent every reciprocal classes by this type of representation. So this is a representation for the symmetric element. This is for the p-reciprocal element, and this is for the mixed case. Okay, and since this is for the Hecke group or modular group, there is a free structure there. So the length of a word, so we can define the word length in it, and that length of a word is the number of generating element, and we fix the generating set of iota and gamma p, where iota is equal to identity, gamma p to the p equal to, and the the length of the word is the number of generating set of the group present in the reduced form. For instance, if that is the reduced form element, so this is the word length. And the length of the conjugacy classes, a conjugacy class of a word is the minimum length of the reduced word present in the conjugacy class. So, so we already discussed that conjugacy classes are one corresponding to closed geodesics. So we can say the geodesic has word length uh, in, co- in in context of word length. So we count to count the reciprocal classes of the Hecke group. We just need to know K, K is another solution of the sum, the solution set of this sum. Okay, so this is the result by Marmolejo that if R2T is the set of reciprocal classes with word length 2T for the odd case, then this R2T is asymptotic to this function, where ck is the constant and rho k is an real number lying in between root 2 and 2. So we proved this a similar version of it for the even case, and for that we need to define that Vigo function. So Vigo function means for f and g real valued function, we define Vigo function like fx equal to Vigo of gx when x tends to infinity, such that if there exists a x naught in that domain and m positive real number such that this condition holds. Okay. So so this is the result by us, me and my PhD supervisor Krishna Bangabadhan. So that an element is said to be a conjugacy class of reciprocal element T, where and P equal to 2R, then this function is a bigger function of this. Okay, where rho is the real positive root of this polynomial and s is the maximum of the multiplicities of the root of P. Okay. And now we'll go to the asymptotic growth, and we will say f and g are equivalent if f is a bigger function of g and g is a bigger function of f. And we consider phi as a complementary distribution function or the standard normal distribution. And so that means phi of x is always positive and for any finite x. Okay, so this is our result for odd e equal to 2r. The Q is the set of reciprocal classes of Hecke group, while with at most a word length. So, this function is associated to that. And if I take r equal to 1, then this is the case of modular group P equal to 3. And since in r equal to 1, this part will not be there, right? Because it's x to the x over 4 and it's also x over 4. So this part will not be there. So eventually, for the corollary, the Basmajian's result. And also we I haven't write down here, but for the primitive case and in general case, they have same growth. Okay, and for this is for the even case, dx is asymptotic to that function, where tx is the set of all reciprocal classes in the Hecke group with water at x, where mu and sigma. And to see the sketch of the proof of theorem 1, we need to mention the center limit theorem, and we have to go for this lemma. We prove this lemma by where provide the summation of p mod of pi equal to Sn, and the Sn, the number of solution of Sn less than x is this. Okay. So by replacing pi's with 2 into ki's mod of ki's plus 1, and for that mu and sigma value will also be changed, and we have to multiply half of it, because for odd case there are exactly two form which look similar to it, and that that will give us the required theorem. This one, this one. Okay, so this is the proof of that theorem one, and I guess these are the references, and yeah, thank you.
All right.
Yeah,
Any
so
questions? Any quick questions?
I'm still a little bit puzzled with
um,
the probabilistic. What is probabilistic? I think these structures they should be kind of like deterministic. How can you explain a little bit how probability enters in your
oh so yeah,
setup?
so so the thing is, here for the central limit theorem, it's it depending on n, right? So that means so if I take this equation, so in that case the n is uh, and I guess the length of this Sn is bounded by x. Okay, and for that n, the central limit theorem can be uh, can be ap- can be applied. Okay, but since we have restriction on that we have restriction. Oh, sorry. Yeah, I should say like so. So what do you want again? Let me let me know. Uh,
Yeah.
Hello.
What is the like what is your probability distribution and why is this thing probabilistic? Like,
Yeah. So my thing. Uh, okay. In that sense, we are considering that uh, the do you want to know what is sample set here, or
yeah, you
yeah,
know,
the sample set are from minus r to r here, minus r to r. Okay, and we are this I mean we are choosing this number as random variable. So here, since they are independent and identically distributed for every xi that represents that pi number. Okay, and since they are mean, you can think it of a dice. I mean, so the dice from minus r to r, right? And then if I take the summation of that xi's, that x that x which is less than Sn. Okay, so this is the thing, right? And the probability, sorry, so the probability of this xn is the number of xn over the whole collection, right? I mean, here it will be
no,
2r.
no, I understand this setup, but I don't
Yeah.
understand how it relates to the to the whole picture you started with, like
Okay.
the
Mm.
like I don't understand what's the probabilistic nature of the initial problem that you that's the connection I'm missing.
Yeah.
Oh,
Is the
I
work on archive,
yeah,
Debattam?
yeah, yeah. It is
You
on
can
archive. Yeah,
show.
Maybe I
Is it?
should look it up. Yeah, okay.
yeah,
Thank you.
yeah, yeah. I'll.
Yeah.
I mean, that will be
It's
the.
fine. You can
It
just
will take.
show the yeah. So that
Uh,
all right. Yeah. It's fine. I think now we can just go through and find out.
yeah, this
All
is.
right. Thank you, Devattam, again for
Yeah.
the nice talk.